Hello and welcome to Embedded Internals. This is second episode of our series Pointer Thinking series. Before learning pointer dereferencing, we must know the answer of how does CPU actually finds data inside RAM. So when we write x is equal to 10, how does the processor knows where x exists? Why do addresses exist? And what is address bus? What is data bus? What really happens when CPU reads memory? This is what we are going to understand in this episode. So uh, imagine a system of 8 GB RAM. In this 8 GB RAM, when CPU has to access our variable that is x, how does CPU locate x? Without address, CPU will not able to find anything. So there must be a location identifier, which is memory address in our case. So every bytes get an address. Address is not data. Address is the location where data stored. So for example, this is the address 1000, and at this address our value 10 is stored, and CPU need address to locate our value. Now the question arises, why addresses are always in numeric form? Why not alphabets or something? So CPU works electrically, which has only two values, either 0 or 1, high or low signals. It doesn't store any x, count, temperature, any label which we give to the uh, variable. Like when we are declaring int x is equal to 10, CPU don't know what x is. At the compiler level, x will be translated into some address. So this is done by the compiler. Every variable get its address, and CPU knows this address, not our label. At the compiler level, size of int, which is usually 4 byte in x86 architecture. So 4 byte memory will be allocated to our variable x by the compiler. Each byte has an address, not the variable. We know that our variable are stored at some address inside RAM, and CPU need address to get the to locate our variable. So how the CPU touches RAM? So the reality is CPU communicate with RAM using the buses. So like we have CPU, we have address bus, we have data bus, and then we have RAM. So now the question is, what is address bus and what is data bus? So address bus carries memory location. When CPU wants to read the address 1000, CPU send this address to RAM. So this is CPU. It will send 1000 to RAM. So when RAM sees this address, read from this address. What database? Database says what value resides at that address. Using the data bus, it return the value 10 to CPU. So we can say address bus locate where in the memory, whereas data bus says what value at that memory. So the communication to and from CPU and RAM, between CPU and RAM, is done by using address bus and data buses. Address bus carry memory location, whereas data bus carry the value. Register versus memory. CPU prefers registers as they are extremely fast. When we are accessing the registers, it is like one cycle, one CPU cycle while accessing the registers. Whereas when we have to access the RAM directly, it might take uh, 50 to 200 cycles. Every address from RAM is stored inside the register, then only computation will take. So this is how CPU perform any computation. For example, when we are saying int x is equal to 10, inside the memory at an address 1000, our value 10 is stored. So at the assembly level, we will see the command move inside one register this address. So at the instruction level, we are storing the address inside the register. So inside the R1, we will have the value 10. In the same example, int x is equal to 10. PTR is a pointer to integer which have the value address of x. So it is like address of x, let us consider 1000 where our value 10 exists, and pointer which exists at some address which contain the address of x. So this is x and this is PTR. So pointer contains the address, and this is exactly what CPU use. That is the reason pointers are very powerful. So what is the address width? It always depends upon bus width. Like when we have 8-bit address bus, 2 to the power 8, that is 256. So 256 byte of RAMs are only addressable. Similarly, when we have 16-bit address bus, then in that case we have 2 to the power 16 bytes of RAM will be accessible. Similarly, for the 32-bit address bus, 2 to the power 32 bytes of RAM memory is accessible. And most of the modern system uses 64-bit of address bus. So accessible RAM is 2 to the power 64, which is a very huge number. Next topic is pointer size. Pointer size is architecture dependent. To get the size of a pointer, we can use size of operator. As it is architecture dependent, on 32-bit machine size is 4 byte. Whereas on 64-bit machine size is 8 bytes. This does not depend upon any data type. So whether the pointer is of integer data type, char data type, float, or any other data type, size of will remain same. Virtual addressing. Modern CPUs don't use physical RAM directly. Instead, when we write any program, we get the virtual address. So inside the program, when you are allocating int x is equal to 10, you will get the address, any address, suppose the virtual address from the virtual address space range, which is if it is a local variable, then it is the stack address. And this virtual address, after MMU TLB translation, is into the physical address, which is actually the real address where the our variable stored inside RAM. Virtual address is fake address. Why we need the virtual address? Why can't our program directly access the physical address? Virtual address provides isolation, security, as well as protection. That is the reason virtual address are required. Why embedded engineer must know about the pointers? As embedded engineers are usually working on hardware, so while programming the hardware, let us take an example, has defined GPIO out. This is a register name, volatile variable. When programming hardware, like this is an example, GPIO underscore out is our register, and this is the address corresponding to that register. So this address is not actually RAM address, it is our hardware address, not RAM. This address is our hardware address. Actual hardware register. CPU can access it directly. So when we have mapped this register in our software, so CPU can directly access this register. Address buses don't care when we send the any address through the address buses. It does not care what the destination is. Destination can be RAM. So for the address bus, destination can be RAM, UART, SPI, GPIO, timers, watchdogs, anything. So every address is accessed via address buses. And this is the foundation of memory mapped input output, memory map IOs, as this is the uh, actual address of hardware registers, and we have mapped this register address directly into our memory, and using the address buses we can access that address and read the value which is present at that address. And this is the concept of memory mapped IOs. We can see that hardware view of pointer is, this is our pointer, any pointer, store some addresses. Address can be of anything, RAM, GPIO, hardware, anything. And then this address is sent through address bus to access the memory. Memory has been accessed. So the address which we have sent through address bus, we reach that address and read the, at that memory location, read the value and send that value using the data bus to the CPU register. This is what really happens when we are dereferencing a pointer. Let me give you the summary of this episode. In this episode, we have seen that RAM is consist of addressable bytes, and every byte has an address, and CPU can access memory using those addresses. So that is, CPU cannot directly touch RAM. It needs address buses for communication. Address bus which carries the memory location, whereas data bus carries the value stored at that memory location, and pointer uses that addresses. So we can say that pointers are software representation of hardware addressing. The pointer which store the address, and we send that address using the address bus, and we read the memory at that address, and whatever value are stored in that address, we send that value using the database to the CPU register. This is what happens when we are dereferencing a pointer. In the next episode, we are going to see pointer dereference internal in depth detail. Stay tuned for same. Thank you.